So just one follow-up thing to this, and which is really the reason why this is titled the way it is. Any thoughts about that exercise? Did you learn anything? There's a lot of waste. As chemistry is practiced, and as chemistry has been practiced for 300 or so years, it is inherently, that is by its nature, inefficient. We use an enormous amount of stuff to make the things we all want and use. And later on, we'll be touching a lot more in depth on energy, but chemists use energy like it's popcorn, like it's free. Okay? They don't pay any attention to energy. And this is an example. The reason we did that is to show you that synthetic organic chemistry, modern synthetic organic chemistry, the things that get made into all the materials that you use on a daily basis, is by nature inherently inefficient. It's wasteful. And it uses a lot of toxic materials. But we'll talk about that later. So we definitely use too much stuff, and hopefully you got that message. And this works. Wonderful. So in this module, we're going to be talking about measures of chemical efficiency. And again, there's a number of drivers and presuppositions about that as chemists, that chemists think about, and that if you've had any chemistry courses throughout your training, you will know these things. And we'll talk a little bit more about E factor and mass intensity. So again, a recapitulation of principle number 2. And important aspects here: designed to maximize the incorporation of all materials used in the process in the final product. What did you notice in that example that we just went through? How much was actually ending up in the product? Almost nothing. In your standard pharmaceutical process, to get a kilo of drug substance, more than 99+% is thrown out. So think about this. You have a $2 billion a year spend, and 99% of that is thrown out. That's big money. So I'm a big fan of asking the right questions. So you're going to hear me a lot of times asking questions, and I want you to focus on the right questions. Ramifications of not achieving that principle is waste and toxics, and that's why the world is in the state it is in. And how do we know if we're achieving that goal? So this is a great quote. It's a science fiction writer. Ursula Le Guin wrote this book, The Left Hand of Darkness, and I love it. Avoid the perfect uselessness of knowing the answer to the wrong question. You always get asked questions, and many times you come up with an answer, but is it the right question? You may come up with the right answer to the question that's being asked, but did you ask the right question to begin with? So in sustainable and green chemistry, make sure that you're always asking the right question. Don't waste your time. This is a graph that all of you who've taken any kind of chemistry should recognize, particularly synthetic organic chemists always are about yield, right? And selectivity, chemical selectivity. We'll talk a little bit more about chemical selectivity to remind you of that. These two measures, I'm not sure how many people have heard them. Those of you who've had green chemistry will have known this. Atom economy was developed by a professor out at Stanford, Barry Trost, and he was an early winner of a Presidential Green Chemistry Challenge Award. It's used extensively. I imagine that none of you really deal with these measures in your training as chemists. This is something that industry obsesses about, but no one else. And a gentleman asked the question about why would industry want to pollute? We don't. It's just that we don't have the right tools. Chemistry is inherently inefficient. I'll keep saying that. The way that we make molecules, the way that we make and break bonds, is by nature inefficient. And we've got to change it. That's up to you guys. This is traditionally how most chemists measure efficiency. It's yield. All right? So it's theoretical over actual. And, of course, it's always A plus B goes to C. There's nothing else in the world that we have to worry about. But again, what you learned in that process is there's a whole bunch of junk that gets thrown in there, and very little of it ends up as C. And oh, by the way, A and B aren't very much of what gets part of the process to begin with. It's usually a very small amount. And yet, I guarantee you that if any of you are synthetic organic chemists, none of you are worried about anything but A and B. Maybe a catalyst because you like catalysts, and we'll have a lot more to talk about catalysts later on. But I want you to go away with the notion that it is a fallacy to be trained as though the only thing that matters is yield. Yield, from a green and sustainable perspective, is the worst measure of chemical efficiency or greenness or sustainability that exists. I'm of the opinion they should just chuck it out. It's a useless metric. So in case you didn't know how I feel about it. Chemical selectivity is something that most chemists spend a lot of time with. All right? Chemoselectivity, we only want one group to react. You know, SN1, SN2, we can talk about electrons being moved around, we can talk about bonds being broken and made. This is chemoselectivity. That's what everyone focuses on. In antioselectivity, stereoselectivity, regioselectivity, I know if you've had organic chemistry, you're all familiar with those terms. Probably not as familiar as someone in the pharma industry because this is the lifeblood of the pharma industry. Why are these concepts important? Mirror images. All of our life depends on stereochemistry. And what is the most important isomer typically? It's the L or R. It's L. Typically it's left, okay? Leave a rotary. That's just turning light, polarized light, okay? So isomerism is extremely important. It is the reason that things are so wasteful, because when you make a racemic mixture and you end up with that racemate and you want to only one isomer, you throw out 50% of what you started with, unless you can re-racemize and get more of the isomer. So I know a lot of this, if you're not a chemist, isn't going to mean a lot, but take away from what I'm saying that there's an enormous amount of waste in making what we make. So atom economy was proposed to measure, I've heard it said that it is a framework, it's a guiding principle to help chemists think about A plus B going to C. All right? And that is all of A and all of B react to form C. In reality, okay, it's a great idealistic measure. In reality, it almost never happens. Almost never. So it's kind of like, do we want a metric that drives us to perfection because we know we can never attain it, or do we want some other measures that actually will help us a little bit more? But that's really, it's a very simple measure. And if you use a linear process, that's all you do. And if you have a convergent synthesis, that's how you calculate it. So again, in most of these talks, you're going to find we're going to breeze through certain slides. You've all been mailed these slides. They're there for your reference. I'm not going to spend a lot of time talking about them. In atom economy, there was another person, also at Stanford, who talked about step economy, Paul Wender. And in my opinion, step economy from a synthetic organic chemistry perspective should have more weight than what it does. And the reason is that the fewer steps you have, the fewer number of isolations, the greener your process is. So if you can do a multi-pot synthesis or a cascade type reaction, which are very common in nature but almost never in the chemistry lab, those are the kinds of reactions you want to do. By a cascade reaction, what I mean is it starts out and it goes way down. And it goes to the product very rapidly in a single pot in very high efficiency. Over here, we have some very good atom economical reactions. A rearrangement, that's a no-brainer. If you can just take that bond and swing it over to here, it's typically a lot easier. An addition reaction is deceiving because inherently you have to start out with a molecule that's at a high energy, okay? One of the molecules. Addition reactions are polymerization reactions. So plastics are typically addition reactions, all right? And what do we make plastics from? They're highly energetic molecules, ethylene, propylene, oxide, things like that. They have strained bonds. So when you start polymerizing it, they just go, all right? Very efficient reactions, but it is deceiving. Diels Alder reactions, so on and so forth. Substitution reactions, that is where you're taking one molecule and replacing it with another or a portion of a molecule. Elimination, Wittig and Grignard. Name reactions, you can look them up. I'm not going to go into great detail about them, but they're definitely not atom economical. So again, Claisen-type condensations, reactions, just a rearrangement of some bonds here. So you're forming the ketone to go to the alcohol, and you've got the double bond there. Very simple reaction, works very well, 100% atom economy, done at reflux. Again, no one ever worries about reflux. We'll talk about that, but that's energy. Okay? And again, as chemists, we don't think about energy, and we really ought to, because mass and energy are correlated, and as much waste as you see, that's how much energy you're wasting. So every time you see an E factor, which is the way it is, think that's how much energy and more that you're using. Atom-efficient addition reactions, again, very simple examples, won't spend a lot of time. Hydrogenation with catalysis, that's deceiving because it's typically going to be done at high pressure and use a platinum group metal catalyst to do that. And we'll talk more about why that's a problem. But from a perspective of atom efficiency, that is A plus B going to C, yes, these are great reactions. Excellent, Diels Alder, excellent way of forming carbon-carbon bonds. This is an important concept to get across because most of what chemists do is we take petroleum in a reduced state and we functionalize it. Nature produces very functionalized molecules, lots of oxygen, lots of nitrogen, lots of sulfur. Those things don't exist in most of the petrochemical type of molecules that we make. So keep that in mind. These are the type of reactions that we all know and love and we're trained in. Wittig reactions, triphenylphosphine, I don't know how many of you have ever heard that. 3 large phenyl groups around a phosphorus molecule. It's used extensively throughout industry. It's a great molecule for them to use. However, you can see that you're throwing away 3 phenyl groups in a phosphorus every time you use this. And it's not going to be done in stoichiometric amounts or catalytic amounts. Typically, the stoichiometry is much greater than 1. All right, that's more than 1 mole of triphenylphosphine. So this is a tremendously waste-intensive process to use. But it helps us make interesting molecules. So I've put in here an example. I'm not going to go through it. But typically, you'll see this kind of thing, 27% atom economy. That's typical. You don't see large atom economies. Occasionally, you'll get up to like 50%. But that's unusual. Most atom economy is bad. When I was at GSK and we were thinking about understanding what makes a reaction green, we started coming up with a lot of different metrics. This is one, reaction mass efficiency. The reason we like this is because it takes into account atom economy, yield, and stoichiometry. All right? And it's not a great measure, but from a chemist's perspective, it's a better measure than atom economy. And that's how you calculate it. And reactants are really important because, again, most chemists don't pay attention to reactants. All the things that are actually reacting in the vessel, they'll only be concerned with A plus B going to C, and everything else is free, right? They don't worry about it. So catalysts, solvents, acids, bases, so on and so forth, they're not reactants. Here are things that should be considered as reactants, but typically many times are not. Mass intensity, we talked about in the last talk. I will just remind you again that it's a great measure because it goes with all of the mass that goes into the pot. And again, if you're working in the lab and you're a synthetic organic chemist, get away from yield, start talking about process mass intensity. Mass productivity is just the inverse, because in the business world, mass intensity is a difficult concept for the business guys, so you have to put it in a percentage, and everyone understands it. However, they go into deep shock when they find out that a reaction, like in the pharmaceutical industry, is less than 1% efficient. They don't believe it, but it's true. E factor or mass intensity, again, we went through this. Why do I have this as a repeat? Most of the world, when they teach the principles of green chemistry, will obsess on E factor. It's the one measure Roger Sheldon did in the early 90s. Everyone loves it. Sitting inside industry, it doesn't get people's attention, because waste, although what Rich said is true, you pay for it once, you pay to keep it and manage it and store it, and you pay for it again to dispose of it. Most people don't worry about that. What they do worry about is that what I was saying earlier on, $2 billion spend for my chemicals, and I'm throwing out 99+% of those chemicals. And some of them are pretty expensive. So I hope that I've taken you through a few measures, and not a lot, of chemical efficiency, particularly the process ones. Pay attention to those, particularly as you go forward. Traditional measures really don't cover. So yield and atom economy really don't give you the right idea. They're really not good metrics from a green and sustainability perspective. They will not ever green your process. They will keep you in the same place that the world has been for at least 100 years in modern synthetic organic chemistry. And we've got to get beyond modern synthetic organic chemistry. Mass intensity, mass productivity, mass-based measures of green reactions are better measures because they are broader measures of what's really important. And again, this is just one principle. It's all about green and sustainable chemistry is all about application of all 12 principles, right? So as we go through the day, these should be building on each other. We haven't talked about hazard yet, and Rich is going to have a couple presentations to talk about that. There'll be some expansions on waste. There'll be some discussions about energy. And what you need to think about is how all these things tie together, okay? The problem is a multivariate one. There are multiple variables, and if you go in and say, I'm going to use this measure and I'm going to call my reaction green, you're only kidding yourself. You have to have multiple measures in order to get it right, okay? They're all important. And as I mentioned at the very beginning, that what you find out when you use these multiple measures is that you're trading impacts. I might be able to get more efficient chemistry, but I have to use a highly hazardous material like an aziridine or an azide to do click chemistry. For those who are synthetic organic chemists, they'll know what I'm talking about. Very efficient reactions, almost 100% atom economy when they go, but no industry will ever use those compounds because they're explosive. They're highly hazardous. You only use them in the lab. The last frontier of the unsafe world is the laboratory. So with that, I'd be happy to take some questions. Yes?
I have a question. I work in the organic chemistry lab over at University, and we have an initiative where we're trying to go green and instead of using reactions and experiments that do this, we're trying to focus on experimental procedures that work better for the environment. And so with that, we implemented at least pathogens last semester that were supposedly greener, but from this standpoint, we did a Gills-Alder in water. And it was under reflux for over an hour, which there is where I'm seeing, the problem inherently in it. So would that be considered for us, would that be a step, instead of a step in the right direction which we thought, or would it just be a step sideways?
So we as humans like to be reductionist, right? We like to reduce things down into little bite-sized chunks so we can understand them and deal with them, right? And you can't reduce green and sustainability down to a reduction, you know, to that small a piece. You have to come back and constantly take yourself back and look at the system and look at the big picture. Because if you don't, you end up optimizing one part and not another. So what I would say is that's a great step forward. It's better than where you were before, running a deals order in water. We'll talk later this afternoon about how you might actually run that reaction in a different way and make it better from an energy perspective, okay? But that's what you have to do, is you have to think of the whole thing and understand that this is a long implementation. We want to start making things a little bit greener bit by bit. I seriously doubt that unless the next Einstein or two is sitting in this room right now, that we're going to make that kind of dramatic step change in the world. We may, I sure hope we can, but more than likely it's going to be these small increments where we have to, you know, make it greener, okay, and make it better than before. And that's really what you need to strive for.